In numerical analysis, Newton's method, named after Isaac Newton and Joseph Raphson, is a method for finding successively better approximations to the roots of a real-valued function. The Newton-Raphson method in one variable is implemented as follows. Given a function e defined over the reals x, and its derivative e, we begin with a first guess xo for a root of the function f. Provided the function satisfies all the assumptions made in the derivation of the formula, a better approximation x1 is. Geometrically, is the intersection with the x-axis of the tangent to the graph of f at. The process is repeated until a sufficiently accurate value is reached. This algorithm is first in the class of Householder's methods, succeeded by Halley's method. The method can also be extended to complex functions and to systems of equations. Description. The idea of the method is as follows. One starts with an initial guess which is reasonably close to the true root, then the function is approximated by its tangent line, and one computes the x-intercept of this tangent line. This x-intercept will typically be a better approximation to the function's root than the original guess, and the method can be iterated. Suppose a b is a differentiable function defined on the interval, a b, with values in the real number so r. The formula for converging on the root can be easily derived. Suppose we have some current approximation xn. Then we can derive the formula for a better approximation, xn plus 1 by referring to the diagram on the right. The equation of the tangent line to the curve y equals e, x, at the point x equals xn is where e denotes the derivative of the function e. The x-intercept of this line is then used as the next approximation to the root, xn plus 1. In other words, setting y to 0 and x to xn plus 1 gives. Solving for xn plus 1 gives. We start the process off with some arbitrary initial value xo. The method will usually converge, provided this initial guess is close enough to the unknown 0, and that e, xo, are permel a0. Furthermore, for a 0 of multiplicity 1, the convergence is at least quadratic in a neighborhood of the 0, which intuitively means that the number of correct digits roughly at least doubles in every step. More details can be found in the analysis section below. The Householder's methods are similar but have higher order for even faster convergence. However, the extra computations required for each step can slow down the overall performance relative to Newton's method, particularly if therefore its derivatives are computationally expensive to evaluate. History. The name Newton's method is derived from Isaac Newton's description of a special case of the method in de analysi per I equations numero terminorum infinitas and indemitidis fluxionum a serierum infinitrum. However, his method differs substantially from the modern method given above. Newton applies the method only to polynomials. He does not compute the successive approximations, but computes a sequence of polynomials, and only at the end arrives at an approximation for the root x. Finally, Newton views the method as purely algebraic and makes no mention of the connection with calculus. Newton may have derived his method from a similar but less precise method by Viatar. The essence of Viatar's method can be found in the work of the Persian mathematician Sharaf al-Din al-Tusi, while his successor Jamshid al-Qashar used a form of Newton's method to find roots of n. A special case of Newton's method for calculating square roots was known much earlier and is often called the Babylonian method. Newton's method was used by 17th-century Japanese mathematician Seki Kawate to solve single-variable equations, though the connection with calculus was missing. Newton's method was first published in 1685 in a treatise of algebra both historical and practical by John Wallis. In 1690, Joseph Raphson published a simplified description in Analysis I Equationum Universalis. Raphson again viewed Newton's method purely as an algebraic method and restricted its use to polynomials, but he describes the method in terms of the successive approximations xn instead of the more complicated sequence of polynomials used by Newton. Finally, in 1740, Thomas Simpson described Newton's method as an iterative method for solving general nonlinear equations using calculus, essentially giving the description above. In the same publication, Simpson also gives the generalization to systems of two equations and notes that Newton's method can be used for solving optimization problems by setting the gradient to zero. Arthur Cayley in 1879 in the Newton-Fourier imaginary problem was the first to notice the difficulties in generalizing Newton's method to complex roots of polynomials with degree greater than 2 and complex initial values. This opened the way to the study of the theory of iterations of rational functions. Practical considerations: Newton's method is an extremely powerful technique. In general, the convergence is quadratic. As the method converges on the root, the difference between the root and the approximation is squared at each step. However, there are some difficulties with the method. Difficulty in calculating derivative of a function: Newton's method requires that the derivative be calculated directly. An analytical expression for the derivative may not be easily obtainable and could be expensive to evaluate. In these situations, it may be appropriate to approximate the derivative by using the slope of a line through two nearby points on the function. Using this approximation would result in something like the secant method, whose convergence is slower than that of Newton's method. Failure of the method to converge to the root: it is important to review the proof of quadratic convergence of Newton's method before implementing it. Specifically, one should review the assumptions made in the proof. For situations where the method fails to converge, it is because the assumptions made in this proof are not met. Overshoot: if the first derivative is not well behaved in the neighborhood of a particular root, the method may overshoot and diverge from that root. An example of a function with one root, for which the derivative is not well behaved in the neighborhood of the root, is for which the root will be overshot and the sequence of x will diverge. For n equals 1/2, the root will still be overshot, but the sequence will oscillate between two values. For 1/2, a less than 1, the root will still be overshot but the sequence will converge, and for a permil 1 yen the root will not be overshot at all. In some cases, Newton's method can be stabilized by using successive over-relaxation, or the speed of convergence can be increased by using the same method. Stationary point: if a stationary point of the function is encountered, the derivative is 0 and the method will terminate due to division by 0. Poor initial estimate: a large error in the initial estimate can contribute to non-convergence of the algorithm. Mitigation of non-convergence: in a robust implementation of Newton's method, it is common to place limits on the number of iterations, bound the solution to an interval known to contain the root, and combine the method with a more robust root-finding method. Slow convergence for roots of multiplicity greater than 1: if the root being sought has multiplicity greater than 1, the convergence rate is merely linear unless special steps are taken. When there are two or more roots that are close together, then it may take many iterations before the iterates get close enough to one of them for the quadratic convergence to be apparent. However, if the multiplicity of the root is known, one can use the following modified algorithm that preserves the quadratic convergence rate. This is equivalent to using successive over-relaxation. On the other hand, if the multiplicity of the root is not known, it is possible to estimate after carrying out one or two iterations, and then use that value to increase the rate of convergence. Analysis: suppose that the function e has a 0 at I plus or minus, that is, I plus or minus equals a0. If r is continuously differentiable and its derivative is non-zero at I plus or minus, then there exists a neighborhood of I plus or minus such that for all starting values xo in that neighborhood, the sequence xn will converge to I plus or minus. If the function is continuously differentiable and its derivative is not 0 at I plus or minus and it has a second derivative at I plus or minus, then the convergence is quadratic or faster. If the second derivative is not 0 at I plus or minus, then the convergence is merely quadratic. If the third derivative exists and is bounded in a neighborhood of I plus or minus, then if the derivative is 0 at I plus or minus, then the convergence is usually only linear. Specifically, if E is twice continuously differentiable, I plus or minus equals a0 and I plus or minus permil a0, then there exists a neighborhood of I plus or minus such that for all starting values xo in that neighborhood, the sequence of iterates converges linearly, with rate log 10a2. Alternatively, if I plus or minus A equals A0 and AA, X, AA permil A0 for ZA permil AI plus or minus, ZA in a neighborhood U of I plus or minus being a zero of multiplicity R, and if AA or A is CR, U, then there exists a neighborhood of I plus or minus such that for all starting values XO in that neighborhood, the sequence of iterates converges linearly. However, even linear convergence is not guaranteed in pathological situations. In practice these results are local, and the neighborhood of convergence is not known in advance. But there are also some results on global convergence, for instance, given a right neighborhood U plus of I plus or minus, if f is twice differentiable in U plus and if, in U plus, then, for each XO in U plus the sequence XK is monotonically decreasing to I plus or minus. Proof of quadratic convergence for Newton's iterative method. According to Taylor's theorem, any function f, x, which has a continuous second derivative can be represented by an expansion about a point that is close to a root of f, x. Suppose this root is then the expansion of f, I plus or minus about xn is. Where the Lagrange form of the Taylor series expansion remainder is. Where I 3/4 n is in between xn and, since is the root, becomes. Dividing equation by and rearranging gives. Remembering that xn plus 1 is defined by. One finds that. That is. Taking absolute value of both sides gives. Equation shows that the rate of convergence is quadratic if the following conditions are satisfied. Sufficiently close to the root. The term sufficiently close in this context means the following: A. Taylor approximation is accurate enough such that we can ignore higher-order terms. B, C, finally, can be expressed in the following way. Where m is the supremum of the variable coefficient of on the interval defined in the condition 1, that is. The initial point has to be chosen such that conditions 1 through 3 are satisfied, where the third condition requires that, basins of attraction. The basins of attraction are the regions of the real number line such that within each region iteration from any point leads to one particular root can be infinite in number and arbitrarily small. For example, for the function, the following initial conditions are in successive basins of attraction: 2.35287527 converges to 4. 2.35284172 converges to a 3. 2.35283735 converges to 4. 2.3528363227 converges to a 3. 2.3528363223 converges to 1. Failure analysis. Newton's method is only guaranteed to converge if certain conditions are satisfied. If the assumptions made in the proof of quadratic convergence are met, the method will converge. For the following subsections, failure of the method to converge indicates that the assumptions made in the proof were not met. Bad starting points. In some cases the conditions on the function that are necessary for convergence are satisfied, but the point chosen as the initial point is not in the interval where the method converges. This can happen, for example, if the function whose root is sought approaches 0 asymptotically as x goes to or. In such cases a different method, such as bisection, should be used to obtain a better estimate for the 0 to use as an initial point. Iteration point is stationary. Consider the function. It has a maximum at x equals 0 and solutions of f, x, a equals a0 at z equals a plus or minus 1. If we start iterating from the stationary point xo equals 0, x1 will be undefined, since the tangent at is parallel to the x-axis. The same issue occurs if, instead of the starting point, any iteration point is stationary. Even if the derivative is small but not 0, the next iteration will be a far worse approximation. Starting point enters a cycle. For some functions, some starting points may enter an infinite cycle, preventing convergence. Let and take 0 as the starting point. The first iteration produces 1 and the second iteration returns to 0, so the sequence will alternate between the two without converging to a root. In fact, this two-cycle is stable. There are neighborhoods around 0 and around 1 from which all points iterate asymptotically to the two-cycle. In general, the behavior of the sequence can be very complex. Derivative issues. If the function is not continuously differentiable in a neighborhood of a root, then it is possible that Newton's method will always diverge and fail, unless the solution is guessed on the first try. Derivative does not exist at root. A simple example of a function where Newton's method diverges is the cube root, which is continuous and infinitely differentiable, except for z equals a0, where its derivative is undefined. For any iteration point xn, the next iteration point will be. The algorithm overshoots the solution and lands on the other side of the y-axis, farther away than it initially was. Applying Newton's method actually doubles the distances from the solution at each iteration. In fact, the iterations diverge to infinity for every, where. In the limiting case of, the iterations will alternate indefinitely between points xo and axo, so they do not converge in this case either. Discontinuous derivative. If the derivative is not continuous at the root, then convergence may fail to occur in any neighborhood of the root. Consider the function. Its derivative is. Within any neighborhood of the root, this derivative keeps changing sign as x approaches 0 from the right, while f, x, aa permel beta zau aax to aa0 for 0 aa zau 1. So f, x, slash f, x, is unbounded near the root, and Newton's method will diverge almost everywhere in any neighborhood of it, even though the function is differentiable everywhere. The derivative at the root is non-zero. F is infinitely differentiable except at the root. And the derivative is bounded in a neighborhood of the root f, x. Non-quadratic convergence. In some cases the iterates converge but do not converge as quickly as promised. In these cases simpler methods converge just as quickly as Newton's method. Zero derivative. If the first derivative is zero at the root, then convergence will not be quadratic. Indeed, then and consequently. So convergence is not quadratic, even though the function is infinitely differentiable everywhere. Similar problems occur even when the root is only nearly double. For example, then the first few iterates starting at xo equals 101, 0.5002503776, 0.2510628828, 0.1275079934, 0.0676719776, 0.0412244176, 0.0327412118, 0.0316423362. It takes 6 iterations to reach a point where the convergence appears to be quadratic. No second derivative. If there is no second derivative at the root, then convergence may fail to be quadratic. Indeed, then, and, except where it is undefined. Given, which has approximately 4/3 times as many bits of precision as has. This is less than the 2 times as many which would be required for quadratic convergence. So the convergence of Newton's method is not quadratic, even though the function is continuously differentiable everywhere. The derivative is not zero at the root, and is infinitely differentiable except at the desired root. Generalizations, complex functions. When dealing with complex functions, Newton's method can be directly applied to find their zeros. Each zero has a basin of attraction in the complex plane, the set of all starting values that cause the method to converge to that particular zero. These sets can be mapped as in the image shown. For many complex functions, the boundaries of the basins of attraction are fractals. In some cases there are regions in the complex plane which are not in any of these basins of attraction, meaning the iterates do not converge. For example, if one uses a real initial condition to seek a root of, all subsequent iterates will be real numbers and so the iterations cannot converge to either root, since both roots are non-real. In this case almost all initial conditions led to chaotic behavior, while some initial conditions iterate either to infinity or to repeating cycles of any finite length. Nonlinear systems of equations, k-variables, k-functions. One may also use Newton's method to solve systems of k-equations, which amounts to finding the zeros of continuously differentiable functions phi rk at rk. In the formulation given above, one then has to left multiply with the inverse of the k by k Jacobian matrix JF, xn, instead of dividing by far, xn. Rather than actually computing the inverse of this matrix, one can save time by solving the system of linear equations. For the unknown xn plus 1 or xn, k variables, m equations, with m, k, the k-dimensional Newton's method can be used to solve systems of k equations as well if the algorithm uses the generalized inverse of the non-squared Jacobian matrix J plus equals a 1, Jt instead of the inverse of J. If the nonlinear system has no solution, the method attempts to find a solution in the nonlinear least squares sense. See Gauss-Newton algorithm for more information. Nonlinear equations in a Banach space. Another generalization is Newton's method to find a root of a functional f defined in a Banach space. In this case the formulation is: where is the Fra-Copyright-Chet derivative computed at? One needs the Fra-Copyright-Chet derivative to be boundedly invertible at each in order for the method to be applicable. A condition for existence of and convergence to a root is given by the Newtonian-Cantor-Rovich theorem. Nonlinear equations over p-adic numbers. In p-adic analysis, the standard method to show a polynomial equation in one variable has a p-adic root is Hensel's lemma, which uses the recursion from Newton's method on the p-adic numbers. Because of the more stable behavior of addition and multiplication in the p-adic numbers compared to the real numbers, convergence in Hensel's lemma can be guaranteed under much simpler hypotheses than in the classical Newton's method on the real line. Newton Fourier method. Assume that is twice continuously differentiable on n that contains a root in this interval. Assume that on this interval. This guarantees that there is a unique root on this interval, call it. If it is concave down instead of concave up, then replace by since they have the same roots. Let be the right endpoint of the interval and let be the left endpoint of the interval. Given, define, which is just Newton's method as before. Then define and note that the denominator has a knot. The iterates will be strictly decreasing to the root while the iterates will be strictly increasing to the root. Also, so that distance between n decreases quadratically. Quasi-Newton methods. When the Jacobian is unavailable or too expensive to compute at every iteration, a quasi-Newton method can be used. Applications, minimization and maximization problems. Newton's method can be used to find a minimum or maximum of a function. The derivative is zero at a minimum or maximum, so minima and maxima can be found by applying Newton's method to the derivative. The iteration becomes multiplicative inverses of numbers in power series. An important application is Newtonian-Raphson division, which can be used to quickly find the reciprocal of a number, using only multiplication and subtraction. Finding the reciprocal of amounts to finding the root of the function. Newton's iteration is. Therefore, Newton's iteration needs only 2 multiplications and 1 subtraction. This method is also very efficient to compute the multiplicative inverse of a power series. Solving transcendental equations. Many transcendental equations can be solved using Newton's method. Given the equation with g, x, and or h, x, a transcendental function, one writes: the values of x that solves the original equation are then the roots of f, x, which may be found via Newton's method. Examples: square root of a number. Consider the problem of finding the square root of a number. Newton's method is one of many methods of computing square roots. For example, if one wishes to find the square root of 612, this is equivalent to finding the solution to. The function to use in Newton's method is then with derivative. With an initial guess of 10, the sequence given by Newton's method is where the correct digits are underlined. With only a few iterations one can obtain a solution accurate to many decimal places. Solution of cos x equals x3. Consider the problem of finding the positive number x with cos x equals x3. We can rephrase that as finding the zero of f x equals cos x AAAX3. We have f x equals a sin x AAA3x2. Since cos x A permil 1 for all x and x3, A1 for A1, we know that our solution lies between 0 and 1. We try a starting value of xo equals 0.5. The correct digits are underlined in the above example. In particular, x6 is correct to the number of decimal places given. We see that the number of correct digits after the decimal point increases from 2 to 5 and 10, illustrating the quadratic convergence. Pseudocode: the following is an example of using the Newton's method to help find a root of a function f which is derivative f prime. The initial guess will be and the function will be so that. Each new iterative of Newton's method will be denoted by x1. We will check during the computation whether the denominator becomes too small, which would be the case if, since otherwise a large amount of error could be introduced. See also, Aitken's delta squared process, bisection method, Euler method, fast inverse square root, Fisher scoring, gradient descent, integer square root, Laguerre's method, Leonid Kantorovich, who initiated the convergence analysis of Newton's method in Banach spaces. Methods of computing square roots, Newton's method in optimization, Richardson extrapolation, root finding algorithm, secant method, Stephenson's method, subgradient method, references, accelerated and modified Newton methods are, Dents, Thomas, Cubics, Chaos and Newton's method, Mathematical Gazette 81, November 1997, 403-408. Strang, Gilbert, A Chaotic Search for I, The College Mathematics Journal 22, January 1991, pages 3-12. Kendall E. Atkinson, An Introduction to Numerical Analysis, John Wiley & Sons, Incorporated, ISBN 0-471-62489-6, Jalling J. Ibner, Historical Development of the Newton-Raphson Method, Siam Review 37, 531 €551, 1995. doi, 10.1137/1037125. Bunans, J. Fra Copyright DAO Copyright Rick. Gilbert, J. Charles. Lemera Copyright Chal, Claude. Sargast Isabel, Claudio Numerical Optimization, Theoretical and Practical Aspects. Universitext. Berlin, Springer Verlag pp. Aziv plus 490 doi, 10.1007/978-3-540-35447-5. ISBN A3-540-35445-X. MRA 2265882 P. Duflard, Newton Methods for Nonlinear Problems. Affine Invariance and Adaptive Algorithms. Springer Series in Computational Mathematics, Volume 35. Springer, Berlin, 2004. ISBN 3-540-21099-7. C. T. Kelly, Solving Nonlinear Equations with Newton's Method, No One in Fundamentals of Algorithms, Siam, 2003. ISBN 0-89871-546-6. J. M. Ortega, W. C. Reinbold, Iterative Solution of Nonlinear Equations in Several Variables. Classics in Applied Mathematics, Siam, 2000. ISBN 0-89871-461-3. Press, W. H. Tucholsky, S.A. Bettling, W. T. Flannery, B. P. Chapter 9. Root Finding and Nonlinear Sets of Equations. Importance Sampling. Numerical Recipes, The Art of Scientific Computing. New York, Cambridge University Press. ISBN A978-0-521-88068-8A. See especially sections 9.4, 9.6, and 9.7. Enders R. 1/4 Lee and David Mayers, An Introduction to Numerical Analysis, Cambridge University Press, 2003. ISBN 0-521-00794-1. Core, Author. Kalu, Egwu. Numerical methods with applications are. External links, Haswinkel, Michiel, ed., Newton method, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Wellerstein, Eric W., Newton's method, MathWorld.